All right, y'all. Welcome to lesson three of my DP chemistry curriculum series. So today we're going to be doing structure 1.1.3, which defines the temperature T in Kelvin as a measure of average kinetic energy, E subscript K of particles. So we're basically going to be talking about the relationship between temperature and average kinetic energy. Our goal is that we're going to be able to interpret observable changes in physical properties and temperature during changes of state, and we should be able to convert between Celsius and Kelvin. Something that we will need to know, the main concept, is that Kelvin is the SI unit of temperature and has the same incremental value as Celsius. So, with all that out of the way, let's just jump right into it. So, when we look at temperature and kinetic energy, the first thing we have to do is talk about our temperature scale. Uh, if you are in a country that uses imperial, you might be accustomed to degrees Fahrenheit, but honestly, it's a terrible system. It's based on some outdated thing on the human body where 100 was body temperature, but really that's kind of like 98.6 degrees Fahrenheit. But even that is wrong because our temperatures are slowly going down, but that's not what you're here for. So, to talk about the real temperature scales, in metric countries, we use degrees Celsius, for which the human body is about 37 degrees Celsius as a starting point. And then in science, we use the SI unit or the System International Kelvin. Kelvin, which is represented by capital K, no degree sign, you'll notice it's not there, just Kelvin, is what we're going to be using for all of science. And anything you do, any calculations, we're going to be using Kelvin. Before we go into that, let's just talk about where Celsius comes from. Well, Celsius comes from water. Our two main points we like to think of are the boiling point of water, which is 100 degrees Celsius, and the freezing point of water, which is 0 degrees Celsius. And so our scale is based on that range. And we can go above and below. We can have negative temperatures, negative 20, for instance, degrees Celsius, or negative 40 degrees Celsius, which has significance because negative 40 degrees Celsius is, I also believe, negative 40 degrees Fahrenheit, maybe? I think so. I think they come together somewhere around there. We can do the math, but then again, I don't feel like it. So we use Celsius and it comes from water. But where does Kelvin come from? Kelvin's a bit more interesting. Kelvin is actually based on the absolute temperature scale, where the lowest value is 0 Kelvin. Okay. Now, we call this term absolute zero. Absolute zero has a lot of significance because when we look at absolute zero, that's where the particles in a substance have no movement. You'll remember that in solids, they still vibrate a little, but at absolute zero, there is no movement. And with no movement, that also means they have no kinetic energy. Kinetic energy is equal to zero. So at absolute zero, particles are not moving. Now that's impossible. We can't really get to absolute zero because particles will always be moving, but theoretically, that's what happens. This also helps us know from this information that particles at higher temperatures, those that comma, have more movement. And same goes for particle with less. And that also means more movement or faster movement also means more average kinetic energy. From this, we can understand that when we look at temperature, well, temp is a measure of average whoops, average kinetic energy. So based on these scales, we know that our temperature is just a measure of average kinetic energy. So one final thing that we have to know is how do we go from degrees Celsius to Kelvin or Kelvin to degrees Celsius? It's quite simple. You take your degrees Celsius, you add the number 273, and you get Kelvin. So if we do some quick examples, what temperature does water freeze at? Well, that's 0 degrees Celsius, which would be 273 Kelvin. If we add 1 degree to that 1 degree Celsius, that would be 274 Kelvin. What you'll notice between these two values is it was an addition of 1 either way. This is what we mean by they have the same incremental value. So we say that's the same incremental value. This is going to become important when we start looking at changes in temperature, where it doesn't matter if you have degrees Celsius or Kelvin, because a change of 20 degrees Celsius, so a change of 20 degrees Celsius is pretty much the same thing as saying a change of 20 Kelvin. And I use delta as a symbol for change. So they have the same incremental value. They go up and down the same way. Going back to our example, we can also convert the other way. So if we have, let's say, 300 Kelvin, well, we could convert that to degrees Celsius. All we have to do is now subtract 273, and we find out that that is 27 degrees Celsius. So it's pretty easy to swap back and forth between them. This is something that you should know how to do off the top of your head. You shouldn't really need any calculations. However, I believe this is still in the first table of equations in your data booklet. Now, moving on, what do we use all this information between temp and kinetic energy? What do we use it for? Well, generally, we use that to create heating and cooling curves. So they're not only used to make heating and cooling curves. Heating and cooling curves are just going to be a really nice way or a way to graph changes in states of substances in terms of energy versus temp. Now, specifically when we're talking about energy here, we're going to be talking about thermal energy, in other words, heat. So like if you put a heat source under a block of ice. Now, what does a heating or cooling curve look like? We're going to start with the most common one, which would be the heating curve of water. We like to use water for a few reasons. My favorite reason for why I use water is because I already know the points of interest on water. And what I mean by that is I know the temperature at which water melts and freezes at, because that is an important part of our curve. Now we have our two axes. We mentioned before that we're looking at energy versus temperature. So those are going to be our axes. I wrote energy first, indicating that I'm going to have energy on my x-axis, and I'm going to do temperature on my y-axis. Now I'm going to use degrees Celsius because I'm doing water, and like I said, I already know what that is. That's 0 and 100. Those are going to be my points of interest. Now, when I draw this heating curve, I usually start somewhere below 0, and I draw a line up to 0. This is actually going to be quite a bit easier if I map out where these points exist at. So I'm going to go ahead and do that first. Just get a nice line for 0, nice line for 100. All right. So when I do this heating curve, I hit from below 0 and I go up to 0. Now, You don't have to be super exact with them. I sometimes like to be, but it doesn't matter too much as long as you show that things start and end at these boiling and freezing points. Now I'm going to indicate that I've done a couple things here, and those things are number one, I have flat regions at the boiling and freezing points. These are very important because at degrees, water can be both liquid and solid, ice and water. And at 100, water can also be liquid or gas. When you boil your pot of water, you'll notice that it's still liquid as bubbles are forming. The other thing you might notice is the length. I have made the distance of the flat region at boiling to be much longer than the distance at melting. And that represents a larger energy required to turn something from liquid to gas than from solid to liquid. All right, so in addition to this, we have a couple things that we need to note on our heating curve. The first one right here is going to be the states of matter. So we have solid, we have liquid, and we have gas. There are exceptions where you can have liquid water below zero and liquid water above 100 or below 100 or gas below 100, like evaporation. But when we talk about heating curves, we don't use those exceptions. Furthermore, at these lines, we have both states. So we have solid and liquid. And up here we have liquid and gas. These areas, these flat areas, are what we call the phase boundaries. So I'm going to put a little key here. So we call these our phase boundaries, where both exist. Now in our other regions right here, this is where we have our regular phases, solid, liquid, and gas. And I'm not going to put a key for that one. They're clearly labeled. So the key part of this that I want you all to notice is that we have energy as our independent variable. So we start at a state of low energy, and as we increase energy, temperature also increases. And so you'll notice that it increases linearly. They have a linear relationship. When we get to a phase boundary, however, energy is increasing, but temperature is not. Then once again, we have our liquid state, and it increases at a very similar rate as to before. And then again, we have a phase boundary. Energy is increasing, but temperature once again is not. And lastly, we have our final state. Now, these should all be the same line. These should all be parallel. I maybe didn't draw it that way, but they should be. So the question is, what is happening at phase boundaries? And a very key aspect of our heating curve is that at phase boundaries, heat, so the energy you're using, heat is used to overcome the attractive forces between the particles. And that's why the temperature doesn't increase. The heat doesn't go to raise the temperature. No, no, no. The heat goes to start breaking bonds in the solid or the liquid state. So it's very important that you keep those areas flat because all that excess heat will always go to increase the temperature. That's also a cool reason why you know that a pot of boiling water is always 100 degrees. Because if any part gets above 100, it becomes a gas and leaves. Also, a cup of ice water, if ice is remaining and not melting, is always 0 degrees. Because any excess heat will melt those ice cubes just a little bit more. All right. Last aspect of this lesson is where does heat go? So when we have solid, liquid, and gas phases, generally a good thing to note is that as we move from solid to gas, we say heat is absorbed. And as we move from gas to solid, we say heat is released or lost. That final clarification is just that we don't say that things are gaining coldness. There's no such thing as gaining cold. There is only a loss of heat, which we feel as a decrease in temperature or something getting colder. All right, well, that's the whole lesson. I hope this helped and have a great day.